Okay, hi Lukas.
Which means, of course, so emission is psi A, dagger is psi A. And with that, one can show that apart from an overall constant that we can just set to 0, for the bosonic part, only the symmetric part of HAB matters. So we assume here HAB is equal to HBA. And in a similar way for fermions, one can show that only the antisymmetric part matters, so without loss of generality, so to say, apart from just doing a total shift of the energy, we assume that this is antisymmetric. Yeah? And with that, we essentially capture the most general bosonic and fermionic quadratic Hamiltonian, which are very well known in many areas of physics. In particular, they play a role in quantum metaphysics as free Hamiltonians, because one can easily calculate the eigenvectors of such operators. We can diagonalize them, and one finds that the structure is just decoupled harmonic oscillators. Now, I should say for bosons, there's the small requirement that you can diagonalize it with Bogoliubov transformations, provided that HAB is a positive definite bilinear form. If one doesn't require positive definiteness in the bosonic part, things can become unphysical in the sense that the Hamiltonian may not be bounded from below. In the fermionic case, of course, boundedness is not really an issue, because even though the Hilbert space grows exponentially with the number of degrees of freedom, it stays finite, and therefore we always have like a finite range of our spectrum. Now, these bilinear forms HAB, they play an important role to construct a representation of first the Hamiltonian itself, turning it into a representation of the algebra, and then taking the exponential of the Hamiltonian to describe time evolution, turning into a representation of the underlying group, which in the case of bosons is the symplectic group, in the case of fermions is the orthogonal group. And so let me just quickly maybe put that on the next slide. H gives rise to this HAB, and this HAB gives rise to a KAB, which is defined as omega AC HCB for bosons and GAC HCB for fermions. And I just remind, so this is bosons, and this is fermions. That omega was the symplectic form and G was the metric. Omega governs the anti-commutation relations on the bosonic system, and GAC governs the anti-commutation relations. So we have for bosons psi A, psi B equal to I omega AB, while for fermions we have the psi A, psi B being equal to GAB. Okay, with that in hand, I can just also mention that a kind of main result of the previous session was that if we define U as e to the minus IH, we get the representation U dagger psi A U being equal to MAB psi B. We used the nice Baker-Campbell-Hausdorff, and this M turned out to be e to the K, where this K is the one here constructed from the H, from the from the small letter H that we used as an input for this Hamiltonian. Yeah, and as K is an element of the Lie algebra, of the symplectic or orthogonal Lie algebra, this M as the exponential is a proper group element of the symplectic or orthogonal group. So now these transformations U, they are called Gaussian transformation. They are the transformations generated by quadratic Hamiltonians. And an important property in the context of Gaussian states is that if we apply such a unitary to a Gaussian state, it stays Gaussian. But in order to understand these properties, I actually need to tell you what a Gaussian state is. And that is exactly what today's session is about. So the definition of Gaussian states. So this is kind of the third part, Gaussian states. Okay, so, and I will introduce a rather abstract definition, but the beauty is that even though this definition is abstract, we can extract all the concrete physical properties, most importantly, the so-called Wick's theorem, in a fully covariant, phase-space covariant formulation. So before I define Gaussian states, I define the 1- and 2-point correlation function. So I define for a normalized state psi in Hilbert space such that psi is equal to 1. I define ZA, that's a vector, which is psi A, psi. And just as a reminder, if you're not completely sure how to think of this psi A, if you represent it in a basis, it consists of Q1 to P1 up to Qn, Pn bosons, and for fermions, we can also call them Qs and Ps, but they are, of course, they describe the Majorana operators. Yeah, so this is clearly this Z is a 2n-dimensional vector in the classical phase space. No, we have that V is isomorphic to R to the 2n, and you can think of ZA describing where what the expectation values of all the linear observables of the Qs and Ps are. And we require that this is equal to 0, because we will focus on Gaussian states that are centered at the origin. For fermions, this is essentially a standard requirement to make them physical, because the only way to have Z non-zero would be to turn it into being Grassmann valued, which of course requires an extension of Hilbert space that you are suddenly also allowed to multiply your Hilbert space vectors with Grassmann variables. And we don't want to go into that because, of course, linear superposition of Hilbert space vectors weighted by Grassmann variables is not a physical state. It can still be used to describe resolution of the identities and things like that, but it cannot be used as a physical state describing a physical state in which quantum systems can be. And for bosons, Z could be non-zero, but it's pretty straightforward to extend it to non-zero once the Z equal to 0 case is understood. And therefore, we will restrict in both cases to Z A being equal to 0. And with that, we can use a simplified version for the two-point correlation function that is psi A. Well, okay, so let me just tell you, the standard definition of the two-point correlation function would be to subtract Z in there, psi minus ZB. But then we use these ingredients where Z is equal to 0 to find an even simpler expression of the two-point correlation function for those psi's for which Z is equal to 0. And just to be precise, let me tell you that this way we can define a general n-point correlation function that has n indices, which is really just psi minus Z A1 up to psi minus Z AN psi. And then, of course, in our case, this simplifies to just psi A1 to psi AN psi. And of course, in general, all of these endpoint correlation functions are completely independent from each other. So knowing just some of them will not allow us to calculate all other ones, because eventually knowing all endpoint correlation functions is more or less equivalent to knowing the state. And of course, for bosons, it's an infinite dimensional Hilbert space, and even for fermions, it's a Hilbert space 2 to the n that grows exponentially with the number of degrees of freedom. So we don't expect that just knowing, let's say, a 2n by 2n matrix, such as C2, that we would be able to describe all states in Hilbert space. However, and that's the beauty of Gaussian states, if we know the two-point correlation functions of a pure Gaussian state, we can extract all endpoint correlation function via Wick's theorem, and that's exactly what we will be proving today. So having introduced the definition of C2, I will go in a little bit more detail. Namely, I will do a decomposition. Namely, so we have C2 AB being equal to psi A psi B psi. And I'm claiming that this will be equal to 1/2 GAB plus I omega AB, where G and omega are real bilinear forms that coincide with the respective forms for bosons and fermions. So that means for fermions, this is the standard GAB. So for fermions, this is fixed, not because this is really just anti-commutation relations, while capital omega is also fixed, but only for bosons. Yeah, so the subtlety here is that essentially G depends on the state psi only for bosons, and omega will only depend on the state for fermions. And that just follows from the fact that we have commutation and anti-commutation relations, which ensures that the symmetric part is positive definite and the antisymmetric part is imaginary. And that might be a nice exercise. So proof that, so essentially for that, you don't even need to make an assumption except that psi is non-zero, that we want to show that GAB is symmetric and positive definite. And second, that omega AB is anti-symmetric. Okay, and you can take here really the definition that GAB is equal to the real part of C2AB, and omega AB is equal to the imaginary part of C2AB. That's one way to do it. So do we have volunteers to try out if you can prove this?
And they are also real valued, right?
Yes, so they are defined as bilinear forms on the on the phase space, and therefore
okay, yeah,
they are real. Yes,
I see. Yeah. So we had the agreement that if nobody will be volunteering, then I will be jumping in. But if somebody would like to draw something, maybe as we discuss, somebody wants to join in. So Lucas, there was the CAB. So should we consider CBA for the task, or is this a step in the proof, or?
Okay, yeah, I can give some hints. So I would recommend to essentially decompose the size into a sum of the antisymmetric and the symmetric part, and then show that one is Hermitian and the other one is anti-Hermitian. That should give that should already ensure that the resulting bilinear forms are real and imaginary.
you want to decompose xi's into symmetric and
okay, yeah.
but you mean this?
Exactly. I
Okay.
want to say that this is equal to xi a xi b plus xi b xi a. That's the first object plus xi. Oh, I guess I did have a 1/2 here, so of course here we also have a 1/2, and that of course will matter here.
Right.
Sorry. No, sorry. There, of course, we need the 2 on that side. And then we need the 2.
Okay,
yeah. So essentially we want to decompose this into 1/2 plus 1/2 xi b minus xi b xi a.
And this you want to call G with a hat or something like this, and omega with a hat?
No.
No.
I don't want to do that, but you're free to do that if you want to. I would be fine.
Yeah, no, just wondering whether they have like some meaning or something.
I mean, it is not a terrible idea to give them names like that.
But just for the calculation, no?
Yeah,
so,
yeah, that is completely fine.
So yes. and then the idea is that GAB psi will be, you had 1/2, or?
Yes, that is correct. Yeah. So probably you want to define it such that there's no 1/2.
And then you wanted GBA is GAB.
Yes. And so essentially the first step is to understand why it's real. And that just follows from the fact that if you look at this, that this is emission. No? Do we agree on that?
No, but so GAB dagger is 1/2 psi AB psi B and psi A psi B plus psi B psi A, and that will just swap, right? And for both bosons and fermions, you said we use that they are Hermitian.
Yes, that is correct.
Okay, so 1/2 psi B psi A plus psi A psi B. All right, so we have this operator equality. And if the operators are equal, they have equal expectation values. So we get this, right? So we get the symmetry out of the hermiticity of the operators.
Exactly. Yes. I mean, I want to remind that essentially, if you want to be mathematically completely precise, you would say that the Hermitian operator is the object that you contract WA VB with your operator GAB. No? This is now a well-defined operator. And then from the fact that G is a Hermitian operator, this contraction will of course still be Hermitian, and therefore this will give you a real number every time that you contract that for arbitrary W and V, and that then shows that the resulting, like if I have this, then this becomes equal to WA VB GAB. and it follows from the fact that the operator is Hermitian for arbitrary W and V, that this bilinear form G is therefore itself a real bilinear form.
Yeah, because if I don't contract it, I show it for like a basis of G, yeah?
Yeah, exactly. If you don't contract it, I mean, you can of course just argue and say, well, my intuition knows that if you express G in a basis, it becomes an array of Hermitian operators, no? And then everything is clear. But if you want to stay basis independent, then you can always deduce its properties from the argument that I just showed, namely that you can contract G with dual vectors, and you get something Hermitian, and then from that all further properties follow.
All right. And Lucas, can you tell me when I wrote down what you said, that for all WA, WB as in
V star?
In V star. Thank you.
Exactly.
Yeah. All right. So we had the symmetry.
Yes. Why is it positive definite?
Now positivity. So in a basis, I mean, we have just the harmonic oscillators. So should we go again by considering this AB hat to show that this one is somehow positive, and then go from that? Or
no, I would recommend to go directly from the inner product properties, namely use the fact that, so my recommendation would be to define the vector W as being WA psi A applied to psi.
Oh.
And then.
All right. Okay, so let's see. So WW. We consider that one, or?
Yes, exactly.
And then some sort of like Cauchy-Schwarz, or?
Yeah, I mean, just write it out what it is.
Okay. Yeah. Okay, sorry. WA, WB, and then psi A hat with a hat, right?
Yes.
Psi. So WA, WB, CAB2 by definition, no? That was it.
Yeah, I mean, here you can also directly use that you have symmetry, and that means that that the symmetric part is exactly the G. So that means you will only get here 1/2 G. I mean, even you could either first show that, well, it just follows from the fact that the other operator was antisymmetric, and there should not be a bar, because W is a real object, no?
Okay, so Siok has some microphone problems.
I have a microphone problem?
No, but like I think he wrote in chat that his mic is off or something like this, so that's why he wrote. But
okay.
have a look in the golden font. So for all VA in V star, I guess, he considered just the symmetric contraction, right?
Yes, exactly. Yeah. So this is a very good argument. So Yeah, I mean, this is almost perfect. The only question is, how do we extract from that it's positive definite? No? So that means that it's only 0 if W is 0. No? Like, how can we show that W itself can not be 0?
Wait, let me write this down.
No, so at this stage we have the argument that this is the symmetric part, and therefore it's equal to 1/2 WA WB GAB. And I guess that's also important that in the notation we would need to put in here a 2 if I see it correctly. But that's of course just an overall factor.
But because CAB was 1/2 GAB plus I/2
exactly
omega AB.
Exactly.
So if so GAB is a little bit like psi A psi B plus psi B psi A.
And expectation value, yes,
and
exactly.
Expectation value, and then we pick up the psi. And for this, we still use hermiticity of psi's, right?
Yeah, yeah. We use hermiticity, and we use the fact exactly that if we contract with W on both sides, of course it's symmetric, and therefore it doesn't matter how we order.
Right. Okay. So those are the kind of calculations that's committed, and now we see this, and now that was done, and that was your question.
Exactly.
So
yeah, so how do we prove that there does not exist any W such that W psi is equal to 0? So how do we show that this is non-zero? And if there are no ideas,
but you said for psi non-zero, yeah?
Exactly, yes.
Okay.
Yes. And of course, what do we need to use? We need to use the commutation or anti-commutation relations. And it's very easy. The argument is W equal to 0 would imply that C2AB is equal to 0. And this is clearly a contradiction, because we know, remember from the last slide, that due to the commutation or anti-commutation relations, either G or omega needs to be the form that comes out of commutation or anti-commutation relations. And that implies there does not exist any W that can make W psi applied to a normalized state psi to be the 0 element in Hilbert space. There's some open questions, or it's not fully clear? Yeah, I guess one can one could also describe it through that logic. I essentially just would say that the quickest argument is to say, if W were 0, then of course C is 0, and that cannot be, because we know that by assumption of commutation or anti-commutation relations of Xi. So essentially it's a property of the Xi that there's no way to contract it with a non-zero W that we get the 0 element if we apply it to Xi. So with that, any questions on that? Is that clear to everybody? Okay. Then the last property was to understand that what is omega, namely that omega is antisymmetric, and that we need to multiply it by I to get a real bilinear form.
Omega is antisymmetric. So should we again use some tricks or just do some pedestrian method like before?
You take the dagger of omega again as in the sense of the operator that you defined right before.
Yes, you can do it this way. Okay. I agree.
And here we were subtracting, yeah?
Yes.
Psi A. A. So AB dagger is equals to psi B psi A dagger minus psi A psi B. I don't put the daggers here anymore. So this is minus psi A psi B psi B.
Yes, exactly.
Psi A. So we have minus omega AB. Yeah.
Yes.
Okay.
So that shows that it's an anti-Hermitian operator, and of course we know that any expectation values when we contract. So if we contract that now with W and V, arbitrary bilinear forms, we will always have an anti-Hermitian operator, and that shows that the resulting bilinear form omega is can be written as 1/2 times I and a real bilinear form. So I guess in our convention we would have a 1/2 here, and an I, of course. No. Yeah, I divided by 2. Exactly.
I have, and here minus B A.
Yes, exactly. Yeah. Okay. Everybody happy with that proof? And there is one very important thing. We cannot prove that omega AB is non-degenerate. For bosons, of course, this follows trivially from the commutation relations. But for fermions, there actually exist states, not pure Gaussian states, but for example, mixed Gaussian states and also certain excited states, where omega could potentially have 0 eigenvalues. Yeah. So at this stage, we do not prove that omega is non-degenerate.
What was the definition? That contraction is non-zero or something like this? But now there's
yeah, I mean exactly that if you non-degeneracy.
Like
no,
Yeah.
usually non-degenerate means that this. No. That
I
was
give you
good.
back. Yeah.
It doesn't take zero values for non-zero vectors contracting.
Exactly. I don't know what just happened. Where?
Page. Oops.
Ah, okay.
Yeah.
No, huh? I don't know
No.
exactly.
What happened? We lost it.
I don't know. Okay. Well, I think it was me probably, but I don't know how to. Okay.
Maybe you clear the drawings. Maybe you can undo or something. Yeah. So Varun switched on, saying it shouldn't take non-zero values on non.
Yeah, I mean the omega AB non-degenerate is equivalent that for all WA that are non-zero, WA omega AC is not the zero vector. That's one way to put it. Another one is in all that the matrix representation of omega has non-zero determinant in a given basis, and if it's true in one basis, it will be true in all bases. And that, of course, can be rephrased as saying that it doesn't have zero eigenvalue in any basis if you take the eigenvalues of the matrix representation. Because, of course, we remember that bilinear forms don't have eigenvalues. Yeah, but my statement is we do not prove that omega is non-degenerate. Okay, so congratulations, that was nice kind of proofs, very quick as well.
That was actually quite instructive, so thanks.
Sure, yeah. So with that definition, I recall, so we have psi to be non-zero. Oh, I guess I wrote it the other way. Oh, no, let's just say psi element of Hilbert space with psi equal to 1. And then we had ZA psi A psi equal to 0 and C2 AB equal to psi A psi B psi equal to 1/2 GAB, which was positive, definite, and symmetric, plus I omega AB, which was antisymmetric. So this is true for any quantum state in Hilbert space, satisfying the first condition that ZA is equal to 0. And now I can give the definition of a Gaussian state. So definition, psi is Gaussian if and only if JAB that is constructed by first taking the omega AC and then contracting it with the inverse bilinear form GCB. So let me just emphasize, G is nothing else than the dual form of G. And for that, of course, it was quite important that just in the previous slide, we proved that G is positive definite, because only positive definite bilinear forms, or only non-degenerate bilinear forms can be inverted. So for omega, we cannot generally invert it, but G, which is positive definite, and therefore in particular also non-degenerate, we can clearly define an inverse bilinear form. And we can use that to define J. And that gives us the definition that psi is Gaussian if and only if J defined in this way satisfies J squared being minus identity, which is the condition that at the very beginning I introduced that states that J is a so-called linear complex structure. And I guess if you have ever learned about Gaussian states, you will be a little bit surprised that this is kind of the compact definition of Gaussian state. I mean, of course, there are many other ones that are equivalent, but that's definitely a one very compact one. In the notes, I actually also give a different definition that I immediately show to be equivalent, which I will now also do. So this implies that the following property is true, namely 1/2 delta AB plus IJAB contracted with psi B applied to psi is equal to 0. And that would be the next exercise, I would say. And there, I'm sure there will be a little bit of help required. Are there any questions at this stage?
So this holds also for fermions, I understand.
Pardon?
Is this both for bosons and fermions?
Absolutely, yes, yes. That the whole point of the framework is to unify the two, and so indeed, it applies to bosons and fermions in the same way.
So I will prepare maybe, I'm putting boxes. So that we keep the definitions maybe.
Mm-hmm.
And yeah, I can undo them with the eraser later. So does anybody want to prove the special quantity? So I don't know, I will start with just writing it out. Psi, that's terrible psi. Okay.
So yeah, so if you're starting with this, then maybe we could just try multiplying this, squaring this. I don't know.
Do you want to go ahead and try to square it? Or
Oh yeah, I could try.
so you're doing the direction that if B holds, then A holds?
Yeah.
So
no, the other way.
Yeah. So so you're saying that you have J squared and then put in what J is and then somehow apply the state to it, or?
Yeah.
Okay, so you're writing?
So.
Okay, I let you. Okay, thanks. Yeah, that's delta, yeah.
Yeah, that's very good.
Looks
And
correct.
from that, of course, we would like to derive a couple of interesting properties about the relation between J, G, and omega.
Yeah, I don't know where to go from here.
I guess we could.
I mean, I can give some hints. Namely, I can tell you it would be useful to prove just from these properties J omega to be equal to minus omega J transpose, and that is equal to G. And in a similar way, it would be useful to prove that J transpose is equal to minus J G being equal to minus omega. See if you can extract that just from the fact that J squares to minus identity.
Okay. So you want to contract J with omega. So we should get G at the end, right? So we can maybe use the CAB.
No, you don't need any. Essentially, so for these equations, I recommend not to use abstract index notation because we always deal just with bilinear forms and linear maps. So that means just get used to the fact that your notation here, for example, J is equal to omega G, and so what Alicia wrote, J squared is omega G being equal to minus identity. And then from that, we can extract various things. No? So I mean, like the first property we can now just multiply with G here from the right. Multiply with G, and we see that this is J, and we immediately see that J times omega is equal to minus G.
Correct. Yeah, I see that.
Which is here the, I guess the minus sign wasn't as clear here. Can be proven there immediately. Yeah. And I see that Siok already comes in a very nice approach on how to deal with the equation for.
So you define this new state. Look at the inner product, and
yeah, I wonder if rather than taking the inner product, you can even just try acting on it with G, and because we already know that G is non-degenerate, and if you're able to show that.
You mean with the G hat, or like
so unfortunately, so I just want to comment on what Siok wrote. Unfortunately, the proof the way you wrote it, I don't think that works. And the reason is that you don't take out the indices in a clear way. Like it's not clear how you can multiply identity plus ij and identity minus ij as matrices with each other, because in principle these are there is still an open index, and if you contract that with an open index, it's also not clear. So I would say that the proof here in orange is not quite right.
Because somehow it implies something for the operator, or
no, just because here we do need the abstract index and see that it still has an open index, and you cannot, I mean, here essentially it's somewhere implied that there is a contraction between the two, but you see that if you put in the indices, you see that there is no way to contract them with each other. Yeah, like because
yeah,
you have two upper indices, it's not clear how to contract them or multiply with each other. Apart from that, it was a pretty good approach. Maybe it is something at this stage that is better done individually. So let me share my notes, and let me just tell you briefly. So okay, let me close.